Yeah, so we'll be doing the chapter stability of control systems. Okay, and the question is, so there are 5 transfer function given, so I'll write them here. First transfer function is okay, and we are asked to find which of these are underdamped, overdamped, critically damped, undamped. Okay, so there are 2 approaches to solve this problem. I'll go one by one. So there are 2 approaches to solve this problem. I'll go over it one by one, right? First, let's follow this approach 1, where we write the denominator, right, the characteristic equation in this form: s square plus 2 sigma omega n s plus omega n square, where omega n is the natural frequency of oscillation and then sigma is the damping factor. So if I write this, right, in this form, so let's say A, if I write in this form, then so omega n is root 30. So in what is this? We are trying to find the sigma, because the sigma will decide which of these 4 category this transfer function lies into. Okay, so the rule is, if sigma is less than 0, it's underdamped. Sigma is greater than 1, sorry, sigma is less than 1, underdamped. Sigma is greater than 1, overdamped. Sigma equals to 1, critically damped. Okay, and sigma is equal to 0, undamped. So what's the sigma here? So 2 sigma omega n equals to 11, right? Omega n is nothing but root 30. So sigma would be 11 by 2 into root 30. This will be greater than 1. So this is overdamped system. Okay. So A belongs to, so let me just 1, 2, 3, 4. Okay. So this belongs to overdamped. Let's check for the other one. So these rules we are keeping in mind, right? And try to map all these 5 to one of these. Here, similarly, you can do this for this one also. I think this will also come out to be overdamped. Now let's try this one. Here, 6 will be equal to 2 sigma omega n, right, in this form. And omega n is 12 because 12. So 6 is equal to 2 into 12 into sigma. So sigma is obviously less than 1, right? So this is 24. So this will be underdamped. This belongs to underdamped category. Let me use. This is 2. This is 1. This also you can solve yourself. I think it will fall under overdamped. Okay. Now let's see this one. S square plus 9. So when S square plus 9, so there is no S term here, right? No. So basically sigma has to be 0. So this is undamped. This is undamped category. And what about the last one? So this will be perfect square, right? S square plus 2 omega n s in plus omega n square. So here the sigma is exactly 1, right? Because if you write this, this will be 20s plus 10 chi square. So this sigma has to be equal to 1. So then this is your critically damped. Critically damped is 3. So this is the Now, so the problem is solved. So I'll give you some insight on this problem, right? So why we are calling it underdamped, overdamped, critically damped, or undamped, and then I'll also show you the approach 2, which I think would be much faster. So when sigma is less than 1, right, what happens? The system looks like this in time domain. It goes like this and then oscillates till it reaches the steady state. So this is what happens for sigma less than 1. For sigma equals greater than 1, right, it will happen like this. It will saturate without oscillating. When it's critically damped, also it's similar thing with that. What happens when it's undamped? When it's undamped, it means that it's a sinusoidal wave. This is for sigma is equal to 0. And now if you see, this is what will happen here. So which one is undamped? For this one, right? So if you find the roots of this, what are the roots of this? So roots of this will be plus minus J3. Okay, which will tell you that it's a sinusoidal wave. Okay, let's follow see the approach 2, then it will be clear. We just find the poles. So what's the pole of this one? The pole is at -5 and -6.
Since the pole lies on the real axis,
and this will be your overdamped scenario, right? Same for this one. Now for this one, what will happen? This one, it will be, what are the roots of this one? S square plus 6s plus 144 equals to 0. So this is giving you, because this term is larger, so some value it's giving, right? So it's a complex conjugate. So whenever there is a complex conjugate, the poles will look like this, and there is a sigma here. So -3 plus some j omega minus omega. So this is your underdamped system. Okay, so when there is sigma will give you the damping ratio, and this in the j omega axis, if it is there, then this will give you the oscillation. Okay, so this is damping, this is oscillation. So this will be basically looking like this, oscillation, but there is a damping as well, so it has to die down. Okay, so this is called the underdamped system. Whereas this one, right, there will be no oscillation, so it has to die down like this. Okay, because there is no contribution from j omega axis, the imaginary axis, right? There is no oscillation. Now let's see for the D case. Yeah, so it's lying on J3 minus J3. That's the poles, right? If you find the roots of that. So there is no damping factor, so sigma is 0, right? And there is only oscillation here. It won't damp. If there was a damping factor, this sinusoidal should be dying out slowly, right? So this is your undamped system. Now what about the other one, the last one? So last one is tricky, right? So S is equal to -10. So here roots, but both the roots are at the same location, so there are 2 poles on the same location. So whenever this happens, we call it critically damped system. Okay, because the damping will be very fast compared to the overdamped system. So here if it's overdamped, critically damped would be much faster. Yeah, so either of the approach you can use to solve this problem, right? Now just to summarize the approach 2, what we do is we draw this sigma and j omega and we try to plot the roots. So whenever there is j omega contribution, we say there is an oscillation. Whenever there is a sigma contribution on the left hand side, we say it's a damping. Okay. So when there is only j omega, so means pure oscillation, that is undamped. When there is only sigma, there is no j omega, no oscillation, so then it's overdamped or critically damped, depending whether the poles repeat or not. If poles repeat in the same location, then it's critically damped, otherwise it's overdamped. When both of these are there, sigma and j omega, right, in complex conjugate form, then it's underdamped system.